ಗುಡ್ ಮಾರ್ನಿಂಗ್ ಸ್ಟೂಡೆಂಟ್ಸ್. ಇವತ್ತು ನಾವು ಸ್ಟಾಕ್ಯೋಮೆಟ್ರಿ ಬಗ್ಗೆ ತಿಳ್ಕೊಳ್ಳೋಣ. ಈ ಚಾಪ್ಟರ್ಗೆ ಇನ್ನೊಂದು ಹೆಸರು ಕೂಡ ಇದೆ, ಸಮ್ ಬೇಸಿಕ್ ಕಾನ್ಸೆಪ್ಟ್ಸ್ ಅಂಡ್ ಪ್ರಿನ್ಸಿಪಲ್ಸ್ ಆಫ್ ಕೆಮಿಸ್ಟ್ರಿ ಅಂತೇಳಿ. ಸೊ ಫಸ್ಟ್ಗೆ ಈ ಚಾಪ್ಟರ್ನ ಸಿನಾಪ್ಸಿಸ್ ನೋಡೋದಾದ್ರೆ, ನಾವು ಆಲ್ರೆಡಿ ಭಾಳ ಸತಿ ನಿಮ್ಮ ಹತ್ರ ಮಾತು ಕೂಡ ಆಡಿದ್ದೀವಿ, ಇದ್ರ ಬಗ್ಗೆ ಡಿಸ್ಕಸ್ ಮಾಡಿದ್ದೀವಿ. ಸೊ ಮೋಲ್ ಕಾನ್ಸೆಪ್ಟ್ ವೆರಿ ಇಂಪಾರ್ಟೆಂಟ್ ಕಾನ್ಸೆಪ್ಟ್ ಈ ಚಾಪ್ಟರ್ನಲ್ಲಿ. ಸೊ ಫಸ್ಟ್ ಪಾಯಿಂಟ್ ಬಂದು, ಸೊ mole means the substance mass of substance containing Avogadro number of particles. So Avogadro number means 6.023 into 10 power 23. So to find the various parameters, we have so many formulas here. So first one is number of moles. Number of moles can be calculated using a formula n equal to weight by atomic weight or weight by molecular weight. Similarly, volume of a substance at STP is nothing but standard temperature and pressure, and the temperature is maintained at 0 degrees centigrade or 273 Kelvin, and pressure is to be 1 atmospheric pressure. And at STP conditions, the volume of a substance is calculated by using formula n into 22.4 liters. n into 22.4 liters. Already we know that 1 mole of substance, volume of 1 mole of substance at STP is nothing but 22.4 liters. So similarly, n number of moles volume can be calculated by using formula n into 22.4 liters. So mass of a substance can be calculated using formula n. N represents number of moles into molecular weight. So number of particles can be calculated using formula number of moles into Avogadro number. Already we know so many points in the mole concept. One mole is nothing but Avogadro number of particles, and its mass should be equal to molecular weight. Its volume should be equal to 22.4 liters at STP, and number of particles is nothing but Avogadro number. Similarly, average atomic weight of an element can be calculated using a formula. So we know that atoms are available, elements are available in nature in the form of isotopes. Isotopes means having same atomic number but different mass number. So by using those isotopes of that respective element, we can find the average atomic weight of an element using a formula atomic weight of the first isotope into percentage abundances plus atomic weight of second isotope into percentage abundance divided by 100. So very important formula for the competitive examination, that is calculation of average number average atomic weight of an element. So using this formula we can find that. And next is percentage composition of an element in its compound. If you take any compound, NaOH, in that so 3 elements are present, sodium, oxygen and hydrogen. If you want to find the percentage of sodium or percentage of oxygen or percentage of hydrogen, we can find by using this formula. So the formula here is atomic weight of that element. So whatever the elements you take and that element, atomic weight into number of atoms divided by molecular weight into 100. So this is the formula used to find the percentage composition of any element in the given compound. Similarly, we have another formula here, relation called molecular formula. So molecular formula can be calculated using formula, empirical formula taken n times. How to find the empirical formula? So empirical formula can be calculated using various steps. So first, in the problem, if they give the percentage composition of an element, so we have to divide the percentage composition by atomic weight, its respective atomic weight, and then we will get a ratio value, and we have to convert that ratio value into whole number. So then we get the empirical formula. So empirical formula taken n times gives the molecular formula. How to find n? N can be calculated using formula molecular weight of that substance divided by empirical formula weight. So whatever the empirical formula weight you got here, so we have to add the atomic weight of those empirical formula. You will be getting empirical formula weight, and in the problem itself they will give the molecular weight. So molecular weight by empirical formula weight gives the n value. If you substitute the n value here, you will be getting the molecular formula. So and one more relation is there here. Using vapor density also you can find the molecular weight. So molecular weight equal to vapor density into vapor density by 2. So similarly, percentage concentration techniques are there here. So already you studied so many points in the solutions chapters itself. So to express the concentration, that is the relative amount of solute present in the given solution, we have so many methods to express. Majorly they are classified into two types, physical and chemical. In the physical methods, we have mass percentage, volume percentage, mole fraction, parts per million. Similarly, in case of chemical methods, we have molarity, molality, and normality. So we have these are the formulas to find the mole fraction of a component, parts per million, molarity is nothing but number of moles present in 1 liter of solution. Number of moles can be calculated using formula weight of solute by molecular weight of solute into 1000 by volume in ml. So similarly here we have another relations regarding molarity, very important relations for competitive examination. Among them, one is a dilution law. So dilution law. So if you mix two solutions together, you will be getting another solution which in which molarity either decreases or increases. It depends upon the dilution. So as the dilution goes on increasing, concentration, that is molarity of the solution, decreases. So this can be calculated using formula M1V1 equal to M2V2. So where M1V1 are the initial molarity and volume of the solution, and M2V2 are the final molarity and volume of the solution. Using this formula, you can find the molarity of a solution after dilution. So similarly, we have another formula called neutralization formula. So by reacting acid and bases together, so that reaction is nothing but a neutralization reaction. So if you want to find the molarity of that neutralization reaction, so we have a formula called M1V1 by N1 equal to M2V2 by N2. So where M1V1 and N1 are the molarity, volume and number of moles of acid. Similarly, M2V2 by N2 are the molarity, volume and number of moles of base. Using this formula, you can find the neutralization, molarity of the neutralization. So similarly, molarity can also be calculated using another formula, very important, that is percentage purity. Percentage purity, that is nothing. Percentage purity is nothing but mass percentage. One of the physical technique to express the relative concentration of solute. So if you take 4% of NaOH, so 4% of NaOH means percentage means 100 grams. In that 100 grams or 100 ml of solution, 4 gram of NaOH is present. So the percentage purity into density D refers density into 10 divided by molecular weight. So instead of density, you can also take specific gravity. So that formula is nothing but molarity equal to percentage purity into specific gravity into 10 divided by molecular weight. So these are the two important relations to find the molarity of the solution using density and specific gravity. So if you mix acids or bases together, so you will be getting another solution. See, this is different from the dilution. So what I am going to tell here is mixture of acid or base, not acid and base. It is acid or base. So if you take two acids together, mix each other, you will be getting another solution. So the molarity can be calculated using formula M1V1 plus M2V2 by V1 plus V2. That is total volume of the solution. So similarly, mixture of acid and base, so that can be calculated formula MaVa minus MbVb divided by Va plus Vb. These are the various formulas to find the molarity and mole fraction, parts per million. So similarly, for the JEE and NEET, we have another important point called normality. So if you want to find the normality, so we have to take, in case of molarity, we take a number of moles by volume in liter. So similarly, in case of normality, we have to take number of gram equivalents. Divided by volume in liter. So gram equivalent can be calculated using formula. So that is weight of solute divided by molecular weight is there here in case of molarity. Instead of molecular weight, we have to take the equivalent weight. So we already discussed that. So equivalent weight can be calculated using various formulas. Equivalent weight of an element can be calculated using formula weight divided by valency, atomic weight of the substance divided by valency. So similarly, equivalent weight of an acid can be calculated using formula molecular weight by basicity. Similarly, equivalent weight of base can be calculated using formula molecular weight divided by acidity. Similarly, equivalent weight of oxidizing agent or reducing agent can be calculated using formula molecular weight divided by change in number of electrons. So using these formulas, you can find the equivalent weight of a substance by substituting molecular weight of that solute divided into equivalent weight. So you will be getting the normality. And you can convert a molarity into normality using formula. So normality is equals to molarity into acidity for bases. Normality is equals to molarity into basicity for acids. So this is what relation between normality and molarity. So till now we saw so many relations here, and these relations are very helpful to solve the various MCQs of this chapter. So let me see one by one. So we have a limited time, that's why we are going to solve only few number of questions here. So we will go to questions now. So the first question here arises. So which of the following pair illustrate the law of multiple proportion? Law of multiple proportion. So we know that law of chemical combinations. There are 5 various important laws of chemical combinations are there. Law of conservation of mass, law of definite proportion, law of multiple proportion. So Gay-Lussac's law of combining volumes, and Avogadro's law. And we are all very familiar with these laws of chemical combinations. And here they given one problem related on the multiple proportion. So multiple proportion means if you take 2 or more elements, they combine together forming 2 or more molecules. In those molecules, one of the element is keeping as constant and another element varying in a ratio of whole number ratio, that is 1:2:3:4 like that. So if you take hydrogen and oxygen, for example, if you take hydrogen and oxygen, 2 elements, when hydrogen and oxygen combines together forming 2 or more compounds, one is water and another one is hydrogen peroxide. The formula of water is H2O and formula of hydrogen peroxide is H2O2. You can see here, in case of water, 2 hydrogens are there. In case of hydrogen peroxide also 2 hydrogens are there. But the oxygen ratio in case of water and hydrogen peroxide varies in a ratio of 1:2. So that is what I am telling you. That is law of multiple proportion. States that if 2 elements are combining together forming 2 or more compounds, so in that compounds, one of the element is keeping as constant and another element is varying in a simple whole number ratio. So among the following pairs, they given two compounds in all the options. So among these, where you will be getting this, where you are going to see this multiple proportion, that is what you have to look here. See, in case of option, answer here is answer B. So in case of second option, you can see here, there are 2 elements are going to combine together to give 2 or more compounds, and among them one is lead and another one is oxygen. Among these 2 elements, you will be getting first formula of the compound here is PbO, lead oxide, and here also lead oxide is there, but keeping one element is constant, that is lead here remains constant, but oxygen is varying in a ratio of 1:2. So that's why option B follows the law of multiple proportion. Are you following? Clear? Okay, we will go to the next question. So atomic mass of an element are usually fractional. Fractional means decimal. So if you take chlorine atom, so the atomic weight of chlorine atom is 35.5. So why these fractional atomic weights are possible in case of an element? That is what the question here we asked. That is, atomic masses of elements are usually fractional because options are there here. So they exist as a mixture of isotopes of different masses. They contains impurity of other atoms. If the presence of impurity doesn't changes the atomic weight of a substance. So that's why option B is not the correct answer here. So similarly, they are mixture of isobars. Isobars also nothing makes any differ in the atomic mass. They cannot be weighed accurately. This is also not a correct answer. So the right answer here is they exist as a mixture of isotopes. You are all very familiar with the isotopes, having same molecular formula but differ in the atomic weight, atomic mass. So as a result of differ in the atomic mass, so you will be getting the fractional atomic weight of element. And already I told in the synopsis itself, that is average atomic weight of a substance of an element can be calculated using a formula percentage abundance of first isotope into atomic weight plus percentage abundance of second isotope into atomic weight divided by 100. So using this formula you can find the average atomic weight, and that average atomic weight may be a whole number or may be a fraction. Why the fractions are available? Because of presence of isotopes. So and the next question here is, so third question, so you just see here, so there is a question like this: for every one, sorry for the disturbance, for every one Cl37, here he given the atomic weight of chlorine atom, one of the isotopes of the chlorine atom called Cl37 isotope. So there are three, that is 1:3, 1:3 ratio is there. There are 3 Cl35 isotope. So chlorine is available in nature in the form of 2 different isotopes. One is chlorine 35 and another one is chlorine 37. Between these 2 isotopes, so you will be getting, so in the sample of chlorine, what will be the average atomic weight of the chlorine? So if you substitute the formula is average atomic weight of an element equal to atomic weight of first isotope into percentage abundance plus atomic weight of second isotope into percentage abundance. Here I taken percentage abundance of Cl37 as 25 and Cl35 as 75, because he only given in the problem that is there is a ratio in between 1:3. So that's why for Cl37 I taken 25% of abundance and Cl35 I taken 75% of abundance divided by 100. So you will be getting an atomic weight of 35.5. So and the next question here is the number of oxygen atoms present in 1 mole. I already told you that mole concept. 1 mole of a substance mass should be equal to molecular weight. Volume at STP should be equal to 22.4 liters, and that 1 mole of substance contain Avogadro number of particles, and that 1 mole of substance containing N into Na number of electrons. So here the given, so the number of oxygen atoms, we have to find the number of oxygen atoms present in 1 mole of oxalic acid dihydrate. Oxalic acid dihydrate formula is C2H2O4.2H2O. C2H2O4.2H2O. We can see here one molecule of oxalic acid containing 4 plus 2, 6 oxygen atom. One molecule containing 6 oxygen atom. As a result, 1 mole containing Avogadro number of molecules. So 1 molecule contains 6 oxygen atom. Avogadro number of particles contain 6 into Avogadro number of particles. 6 into Avogadro number of oxygen atoms. 6 into Avogadro number of oxygen atoms. You are already very familiar with the Avogadro number. That is the Na equal to 6.023 into 10 power 23. So that's why, so the number of oxygen atom present in 1 mole of oxalic acid dihydrate is 6 Na. Why? Because one molecule of oxalic acid dihydrate contains 6 oxygen atom. Avogadro number of molecules contain 6 into Avogadro number of oxygen atoms. So next question is total number of atoms present in the 34 gram of ammonia. 34 gram of ammonia atoms. We have to find the atoms. In the before question he given only for oxygen atom, but here they given all. We have to consider all the atoms here. All the atoms. You can see that. So you have to find the number of moles first. Number of moles. The weight they given here is 34 grams and molecular weight of ammonia is 17. So that's why you will be getting 2 moles. Is birthday 2 moles. So here the option solution will be like this. So 17 gram of ammonia contains 17 gram of ammonia contains 17 gram means 1 mole. 1 mole containing Avogadro number of molecule. Avogadro number of molecule. So 1 molecule containing 1 plus 3 4 atoms. 1 molecule containing 4 atoms. Avogadro number of particles containing, so 4 into Avogadro number, that is 4 into 6.023, that is 24 into 10 power 23 number of atoms. So similarly 34 gram of ammonia contains question mark. So see, by seeing the question itself, you can decide that. So 17 1 mole containing these many atoms, as a result 34 gram containing how much number of atoms. If you cross multiplied it, it becomes 34 into 24 into 24 10 to the power of 23 divided by 17. So you will be getting 48 into 10 power 23. That is option C is the right answer. So if we go through the next question, sixth one. So the mass of one molecule of substance in gram. The mass of one mole of substance mass should be equal to molecular weight. Hence, it should be the answer should be molar mass. Easiest question. And next here is the compound containing two elements, that is X and Y. A compound which containing two elements, those are X and Y. So in a ratio of 50% each. 50% each, that is X is also 50%, Y is also 50%. He only given the percentage abundances of X and Y, and he is going to ask, and I also given that atomic mass of X is 20 and atomic mass of Y is 40. Atomic mass of Y is 40. What is its simplest formula? Simplest formula is nothing but empirical formula. I already told you in the synopsis itself how to find the empirical formula. So we have to divide first the given percentage abundances by atomic weight. You will be getting a ratio. We have to convert that ratio into whole number. You will be getting the empirical formula. If you go through the solution, so X and Y are the two given elements in this formula or in this problem. So the percentage abundance of X is 50 and percentage abundance of Y is also 50. First I divided that percentage abundances by respective atomic weights. So atomic weight of X is 20, atomic weight of Y is 40. If you divide these ratios, you will be getting 2.5 and 1.25. So these are not the whole number, these are the ratios. We have to convert this ratio into whole number by dividing into a simplest number between these two. The simple number is 1.25. So that's why I divided both the 2.5 and 1.25 as 1.25, 1.25. So here you will be getting 2 and here you will be getting 1. Hence the formula, simplest formula of the compound is X2Y. X2Y. Hence option is B. So the next question here is, a solution is made by dissolving. Here we are going to prepare a solution by dissolving 49 gram of sulfuric acid. 49 gram of here sulfuric acid is the solute in 250 ml of water. The molarity of the resultant solution is. The molarity of the resultant solution is. How to find the molarity? Molarity equal to number of moles divided by volume in liter. It can be also calculated using formula weight of solute by molecular weight of solute into 1000 divided by volume of solution in ml. So molarity equal to weight of solute, they given 49, molecular weight of sulfuric acid is 98 into 1000 divided by volume of solution is 250 ml. So you will be getting 2 molar. 2 molar. So this is the option A. So next question is the final molarity of the solution made by mixing 50 ml of 0.5 molar HCl and 150 ml of 0.25 molar HCl. See, both the components, whatever they mixing here, two solutions they are going to mix here, both are HCl. That is acids, mixture of acid. Is a mixture of acid. To find the resultant molarity, we have a formula called polarity of mixture of acids equal to, I already told you, M1V1 plus M2V2 divided by V1 plus V2. So first solution here is 50 ml of 0.5 molar HCl and second solution here is 150 ml of 0.25 molar HCl. So this is V1 M1 and this is V2 M2. So if you substitute here, so if you substitute mixture of acids equal to, so first solution is 50 ml of 0.5 molar, so that is V1 is 50, M1 is 0.5 plus second solution here is 150 ml of 0.25, V2 is 150, M2 is 0.25 divided by overall volume, total volume of the solution here is given here is 250 ml. So that option is, so you will be getting an answer 0.25. So option here is D. So sorry, that option is there far away. Okay, no problem. So next here is last one. So which mode of concentration does not change the temperature? So actually the concentration techniques, whatever I told in the beginning of the class itself, we have so many methods to express the concentration. Among them, various physical methods are there, chemical methods are there. So among all these concentration techniques, where the volume is present, those are temperature related. Where volume is not present, they are temperature independent. We already discussed these things in so many times in the solution chapter itself. So here is asking that, so concentration technique which does not change with temperature. Means it is temperature independent. So where volume is not present, that is temperature independent. So here is given molarity, that is number of moles divided by volume in liter. Volume is present, it is temperature dependent. Similarly, normality, that is number of gram equivalents by volume in liter. Here also volume is present. Molality was calculated using formula. So number of moles divided by weight of solute in kg. Weight of solvent. Here volume is not present. So that's the reason this molarity is a temperature independent. I told you 8 concentration techniques: mass percentage, volume percentage, parts per million, mole fraction. 4 physical techniques: molarity, normality. See, these are the chemical techniques. Among these, mass percentage does not contain volume factor, it is temperature independent. Similarly, parts per million also does not contain volume factor, it is also temperature independent. Mole fraction also does not contain any volume factor, it is also temperature independent. Similarly, molarity also does not contain volume factor, hence it is also temperature independent. So these 4: mass percentage, parts per million, molarity, mole fraction. So these are the examples for temperature independent concentration techniques, while molarity, normality, volume percentage, these are the examples for temperature dependent concentration techniques. So finally I will conclude this chapter. So this chapter is very important for your competitive examinations. Go through with all the formulas of this chapter. So this chapter can be divided into various parts. So in the first part we have a introduction part, that is matter, laws of chemical combinations, like that. Based on, you have plenty of formulas, you can solve it. And next next one is stoichiometry or mole fraction. So I given so many formulas here. So among those formulas you can solve plenty of questions. And finally concentration techniques also there. So kindly go through with all the points of this chapter and solve so many problems. You may get the idea. So thank you, students.